So yeah, in the week 5 folder, there are like 2 files, discussion 10 and final preparation questions. So we will first like go over all the concepts in about like half an hour, and then we will try to go over like some of the preparation questions. Some of the questions actually like I will like illustrate some of the ideas in the sample final, and I think like some of my other like colleagues will cover like very detailed about the sample final. I will like make some like I have like some extra questions that you might find very useful like when you are trying to solve like a similar question. So okay, so let's get started. So basically, let's like open the discussion 10 file. Basically, it's a PDF, right? And we're gonna review like something very important concept. Basically, what we have covered like pathfinding algorithm, basically graph algorithm, and then in amount that we have like depth first search, breadth first search, and digestra, some kind of like topological sorting, and we go over like a 3D algorithm, and then it's divide and conquer, and final is dynamic programming. So I covered dynamic programming because like I should cover like divide and conquer in a previous discussion session, but I cover like I was talking about dynamic programming. So if you have any if you like want to know more about dynamic programming or related questions, go back to discussion 8. I think there's a video about that. There's a recording about that. So let's get started. Concept review, like pathfinding algorithm. Like, so first context, the first thing we need to know is we assume that autographs are simple, that autographs does not have any self loops. And also we need to pay attention to the question, like what does question specify? So when you see a question, like you need to like first circle out like, is it a directed graph or an undirected graph, right? Is it a cyclic or potentially cyclic? Is it like, does it have like positive or edge weights or non-negative edge weights, or it doesn't have any edge weights? This is the first thing you need to pay attention to. And second thing is, do not make any assumption about the structure of the graph that is not mentioned in the question. So I receive a lot of questions in office hour saying, can we assume like this is a DAG, or can we assume there's only one source? No, just if the question didn't provide you extra information, just assume the graph is just assume the structure of the graph as general as possible. Do not make any like other like extra assumptions about the graph. This is very important. And also, you're very recommended to use any algorithm that has been covered explicitly in the lectures. So you can assume all the algorithm given the lecture is correct, are correct without proof, and you can assume the runtime, the time complexity given the lecture is correct without proof. So a very good example is like sample final question number 2, right? You're using reduction. I mean, you can use modification to modify your own depth first search algorithm, but you have to write that down. Like you have to implement it on your own, and you might make some mistakes. So if you can use the black box provided during the lecture, then use it. And if you're pretty confident, say I'm good at like designing an algorithm, and that's okay, right? It all depends on you. But my suggestion is use the black box. And this is the same in software engineering as well. You just try to use like a very mature algorithm that has been tested, that has been confirmed by other people. And this is usually a good habit instead of like building your own version of algorithm. So let's take a look at depth first search. It's a last in first out way of like dealing with objects. So we basically use a stack data structure for implementation, and you can also use like basically use recursions. There's no difference between these two. Basically, just some minor differences. Time complexity O V plus E, but pay attention when it is a tree, E equals to V minus 1. The number of edges equals to number of nodes minus 1. So pay attention to that. When it's a tree, you cannot write OV plus E, otherwise you'll get some points off. And basically depth first search solves reachability and searching problems. And also you can use pre and post number to find strongly connected components in a graph, basically creating a meta graph. And this is related to the topological sort. So basically this is like what we have covered doing for depth first search. And for breadth first search is a first in, first out. We use a Q data structure for implementation. Again, time complexity is the same, but pay attention to the tree, to like the trees. It's a kind of special condition if it's a tree. And it basically solves minimum distance, like minimal steps problems with unweighted graph. And if it's a weighted graph and the weight is non-negative, we have non-negative edge weights. So basically it's like finding shortest path. We use digester algorithm. Basically it just change the queue to a priority queue when we like always look for the nearest neighbor, right? And yeah, this is basically what we cover so far about breadth first search. So I think like for the graph problem, it would be like in the first two problems, not very hard, and you guys don't need to worry about that. But since you have like 1 hour for each one of the questions, so you can just save some time. I don't think you can save some time for future questions. So let's go move on with divide and conquer. I think like yes, because definitely, because you can see like if it's a tree, right? Then basically what is a tree? A tree is basically a special kind of like a graph, like the number of edges. You only have like number of edges equals to n-1 if you have a tree. And so v plus e becomes like v plus v minus 1 to v. So basically, yeah, it is OOV. And pay attention to that. When it's a tree, if you write OV plus E, you'll lose some points. And also, some of the tips we have is efficiency is quite important when you're doing like when you're like doing your final. So if you found a very simple algorithm but runs in O(n) square time or even linear time, and if there's a better if there's an algorithm with better time complexity, then you will still lose some points. And it depends on like and all it depends on. I mean, if your algorithm is very like a very naive question algorithm, basically a brute force algorithm, then you will lose like maybe half of the points, even if your time complexity analysis is right, your proof of correctness is right, and your algorithm implementation is right. This is something you need to like pay attention to. And so let's move on. Like divide and conquer. Let's talk about like divide and conquer first. Just 1 second. Yeah. So how do we build like divide and conquer? So basically, we build recursion tree to break a big problem. Runtime. Okay, I will probably cover that later, like when we're like dealing with like, I think the runtime is OE log V, right? So let me just I'll cover that later when we're like talking real questions. So for divide and conquer, so how do you build like a divide and conquer question? So you build a recursion tree and then you break bigger problems into smaller subproblems. You solve each one of the subproblem at the leaf node, and you combine subproblem solutions for big problem solutions. So basically, like for divide and conquer, it's something similar to like the binary search, where you divide a bigger problem into a small problem, and you solve like each one of the smaller problem and keep applying this recursive functions until you reach the leaf node, and you go back, and yeah, and like the key part is probably about like how do you combine each subproblem solutions for a bigger problem solution. So for merge sort, like after you have like two sorted half, how do you combine these two halves, right? This is basically what you need to consider about when you're like dealing with like divide and conquer problem. So for divide and conquer, how do we estimate the complexity? It's basically, there are two ways. Basically, the first way is to build a recursion tree and write a recursion relation and draw out the uh, recursion tree if necessary. So if you can apply master theorem, then do that. You don't have to do anything else because master theorem, this is something that has been confirmed correct. And otherwise, you have to draw a recursion tree and use a relationship among the depths, the number of leaf nodes, the branching factors to estimate the time complexity without the master theorem. So the master theorem is basically, I think it's open book, so you don't have to memorize that. But when does like the master theorem fail? When the number of children at each node is not fixed. So here's an example, like if Tn equals 2 to the power of n, Tn over 2 plus n to the power of n, then you cannot use that. And also for each node, it cannot have less than one subproblem. And when you're having like this kind of situation, master theorem does not apply. So be very careful about that, because I think oh, by the way, for the final, you will not require to to answer any kind of question that will need drawing. So basically, you will not, that means you will not encounter a problem that will require you to draw a recurrence tree. Okay, so let's move on to like greedy constant review of like the greedy algorithm. So basically, how to use like greedy algorithm. So greedy algorithm is like we break a bigger problem, we break a larger problem into smaller subproblems, and then we pick the best option for the small problem. And so basically, it is like we decompose a bigger problem and we make like the same optimal, like we apply the same strategy at each one of the subproblems. And then we use like constraint limit for choices for next small problems, given what we have already have. And we keep going until we have solved all the subproblems. And final step is combine the solution to solve the big problem. So I think for the final, and probably, I guess, and it will be very similar to homework 3, there's a homework 2 or homework 3, like question 3, question 4. So basically, you will be provided with a candidate strategy. You don't have like to figure out your own greedy algorithm. So the main point is about how to prove the greedy strategy is optimal. So I think probably you will be provided with a greedy strategy, and then you will see if it's not optimal. If the greedy strategy is not optimal, you're asked to provide a counterexample. Otherwise, you need to prove it is optimal. So I think like there are mainly 3 or 4 ways of proving that, but I really I really like prefer exchange argument and greedy stays ahead. So I think this is the two most common ways to prove like the greedy strategy. Yeah, I think the practice exam is not hard. I mean, if once you spend a lot of time and try to understand the notations of each line, like basically understanding the question, and is quite hard. And after that, I mean, the question itself is not that kind of hard, except like the notation is a kind of nightmare, because like VJT, there's little the notation is very bad, like not bad, like it's very complicated, very hard to understand. So the actual final will be yes, the notation. So the final, the real final will not be that kind of hard. Will be actually it will be easier than the practice final. So don't worry about the final too much. I mean, at least as long as you like know the concept and like do the homework, finish the homework correctly, and go through all the lecture videos, I think you will be fine. And so when you're like, so basically, I'm here to like basically talk about like exchange argument and greedy stays ahead. So you're given like a problem instance I, and you call greedy strategy, and we call G as a greedy strategy solution to I, and we call O as other solution or other strategy to I. And we must show that value of GS is larger than the value of OS, and the cost of GS is less than or equal to the cost of OS. And using exchange argument to prove optimality, it's basically you define your strategy or your solution, GS and OS, and you compare GS and OS. Like, are they different because the GS has some elements that are not included in the OS, or are they different because GS has some elements that is different, that has a different order in OS? So the first step is to exchange the first step that is different in OS and GS, denoted as OS prime. And this is basically the first step. And the second step, I think I missed the second step here. The second step is to basically show that OS prime is valid. I will basically cover that also later when we see like an actual question. And OS prime, you need to show that OS prime does not conflict with any constraint that the question has. And the third part is use the previous argument. And once you show, then the next step is to show that OS prime is at least as good as OS. So you use the previous arguments as an inductive argument. OS1 agrees with the first greedy algorithm, and then we say OS2 agree with the first two greedy algorithm, and we can say OST agree with all the greedy algorithm, and OST is just basically greedy strategy or greedy solution. And use like the induction step to prove that value of OS1 less than or equal to value of OS2, blah, blah, blah. And here you are, here we go. And for greedy stays ahead, it's the one that I like to use more often. So basically, you define your solutions GS and OS, and you define a measure. This is, you define a progress measure, and this is usually the hardest part. The progress measure that needs to relate to each choice that the greedy algorithm makes to construct GS and OS. So basically, what is a progress measure? You want to show like a kind of like the way to show that the GS is usually the GS is will always be better than OS, and this is like the hardest part for greedy stays ahead. And I will show an example about like different way of defining a progress measure will decide whether your proof is right or not. And for each step, use the induction to show that the cost of the GS is always at least as good, if not better than the cost of OS. And so basically, this is everything about the greedy strategy. I'm sorry, greedy algorithm. And so the last step is dynamic programming. So for dynamic programming, the first thing is, what is it, right? It's basically backtracking plus memorization. It's kind of similar. If you like, I'm not sure, professor, if you like go over, if you remember like the first thing we covered in the lecture is basically Fibonacci sequence when fib n equals to fib n minus 1 plus fib n minus 2. It is basically kind of like kind of similar to like a backtracking concept. Basically, you just go deeper and deeper, but you do a lot of like overlapping computations, something you have computed before. You don't want to compute it again, so you use like a matrix to like store the value that you have already pre-computed. So how do I create a DP algorithm? You create a recursive backtracking algorithm first. The recursive formula, you basically recreate a recursive formula that solves the question. And the second step, you define the subproblems in the recursion tree. And then the key part is you create like a DP or like a matrix to store the answer to the subproblems that has been solved before. And the last step is to assemble all the matrix entries into a larger solution. So if you go over like the last practice final questions, it's basically we have like a backtracking algorithm first, right? And then we figure out a way to store all the value that has been pre-computed before. We use a 2D matrix to do that. And one thing like dynamic programming is important is you need to figure out a way, you need to figure out an order to solve all the like the subproblems. Like this way the future subproblems can use the result of the previous subproblems to decide which is the optimal choice. This is very important. And when you're like designing like dynamic programming algorithm, be careful about the following things, like clearly state each subproblem and clearly define each entry in your matrix. Solve all the subproblems as I mentioned in a specific order that is consistent with the question. And usually the time complexity is kind of easy because it's basically the number of cells in the matrix times the number of cases you need to evaluate to compute at each cell. So I think backtracking is basically brute force. So let me just give you an example. So for example, if we want to find like the combination from like a combination from 1 to n, we're given like numbers 1 to n, we want to find all the combinations, then it's basically backtracking. So basically you need to go over every single situations, and there is no other way. There's no other way for you to not like use dynamic programming. So because you have to go through every single possibilities to get the answer. So this way when you're definitely use backtracking. And if we take a look at the practice final question number 5. So basically this is backtracking. And we can also consider it as brute force since we basically consider all kind of scenarios, right? I think because I'm not responsible for this part of the question, I think you all have like one dynamic programming question, and probably it will be decomposed into different parts. So basically, you design a backtracking algorithm, then you try to update it. I mean, like how to say that? You try to update it, upgrade to a dynamic programming using memorization. This is what you'll probably encounter during the actual final. So if you want to get just know more about like dynamic programming, I covered like two questions I think related to dynamic programming in the last discussion session number 8. You can find the recordings, also the materials, the lecture the discussion slides in that folder. So feel free to check it out. And so basically this is everything related to the concept review. So let's switch to the second. Oh my God, my computer is getting a little bit overheated, so I probably need to turn down the video. So let's start looking at the practice final questions. Let me see. Practice final problem. So we go over like basically each one of this problem, each one of this type of problems. So the first is basically graph algorithm. So let me start sharing my screen here. Okay, so like let's just take a look at the sample final question 1. It's just basically related to depth first search and algorithm. I think the first question is kind of easy since basically true or false questions, and you need to like give some explanations about that. So the first question is definitely true. Just pay attention to what I just mentioned. If a dense graph, that means number of edges is at most v squared. It's like big O of v squared. So the time complexity is O of v plus v squared, which is v squared. If it's a tree, then it's definitely O of v. So pay attention to that. And the second thing is, if a connected undirected graph has 2 edges that both have minimum weights, then the graph has 2 distinct minimum spanning trees. Then I think you can the solution gives like a good counterexample. The third one is basically if you perform a DAG starting at a source vertex, then all the vertices will be marked visited. There are like different situations. Well, if all the like the if it said it only said it's a DAG, it doesn't say it's connected, right? There might be some kind of like single node that is not connected with any one of the nodes in the graph. And this is basically something what I mentioned earlier, that do not make assumptions on the structure of the graph. If it's not, if the question doesn't say if the auto nodes are connected, then there might be a chance that one of the node is not connected with any other nodes in this graph. So pay attention to that. And also, like, if I mean, like, if there are two sources, also you cannot like do that. And this is kind of like and the question I prepared is basically kind of like a follow-up question for question 1C. So I will give you guys like 3 minutes to take a look at it and try to see like the steps you need to take to go through the single question. Oh yeah, no. I mean, like, take a look at the question that I prepared, like practice final problem, in the file practice final problem. The question 2, like it's kind of like a follow-up question for question 1. And by the way, about like the time complexity for the digestras. So as I mentioned, the time complexity basically largely depends on the data structure that you use. So for me, I usually for convenience, I usually use like sorry, I usually use the heap, which is a priority queue. And for a priority queue, I mean, initializing the priority queue is basically O of n. I'm sorry, O of n linear time. There's a way of doing that linear time. I think it's doing that from back of the priority queue. If you already have all the elements of that queue, and inserting definitely take O log n, where n is the size of the queue, and deleting is the same, O log n. So consider like digestra is a kind of modification of breadth first search. Well, except that we use a priority queue instead of a standard queue, right? The priority queue, like the poll function, which is the poll function, which is getting the top element, basically will take all log v time, where v is the number of vertices inside this graph. While inserting is the same, if pushing it to the queue will also take O log v time. So basically, it's a kind of like the modification of like using standard queue. Like while like using standard queue is basically pushing it is O of 1, while like getting the first top element is O, it will take constant time as well. So given that, like the time complexity using binary, I think the time complexity using binary heap is basically O v plus e times log v. I think because like before like before the BFS basically is v plus e, and right now since we use a different queue for that, we use a priority queue, and the priority queue like for each like kind of like the operation, it will take all log v time. And this is so binary heap will have like OV plus E log V time complexity. And so basically when you're like during the exam, you do not need to know what exactly you don't have to prove like the time complexity for the digest rate is correct. You basically just use the result that has been proved during the lecture, and the time complexity actually largely depends on the data structure. So yeah, and I haven't used like Fibonacci heap. I'm not quite sure about the inner structure of the Fibonacci heap that much, so I can't give you like very detailed proof for that. But using binary heap is definitely OV plus E log V if you consider it like a different kind of queue and a modification of the BFS algorithm. Okay, so I think probably everyone have gone through the question 1, right? So given a directed graph G, and we want to determine if there is a path, and remember, not necessarily a simple path. There can be a loop. We can just keep going this loop, right? And that can pass through every vertex. So if we take a look at graph G1, right? So basically, graph G1 is definitely, we will return false, since if we start at 1, then we can only go through 1, 0, 4. We cannot visit 2. But for G2, we can go through like this. We can go through 1, 2, 3, 4, and we go back to 2 and 3 and 5. This is what I mean, not necessarily a simple path, because we can go to a single node twice, right? And at the first glance of the questions, you'll probably think it's a kind of hard, kind of abstract, like how to find like a single path. So the key point of algorithm designing is to basically decompose, like turning an abstract idea, an abstract question into a more like concrete and more solvable question that we can apply our knowledge and our models, the knowledge we know on it, right? So first thing is try to think of the graph-related algorithm that has been covered during the class, right? Especially for directed unweighted graph. Depth first search, breadth first search, topological sorting, transform directed graph to meta graph. And notice that if there's an SCC, like a strongly connected component in the graph, we can always find a path that passes through every single vertex inside a strongly connected component. This is the key point. So as you can see in graph 2 and 3 and 4, they are inside a strongly connected graph. Yes, we can make a meta graph, right? And a meta graph is what? Is a DAG, right? Then the question is really simple. It's basically we turn this directed graph to meta graph, and you don't have to like write specific specific details about how to create a meta graph. Use it as a black box. It's guaranteed to be correct, right? So we turn it into a meta graph, and then we find a source SCC of that meta graph, which is like we find a source SCC. If there's more than one source, right, then we return false. Correct? If there are 2 sources and 2 and more sources, then if we since the definition of a source is it doesn't have any incoming edges, right? So we cannot go from any single vertex to that source. So if there are 2 and more sources, it's impossible. Return false. Correct. And we run the DFS, right? Because we didn't mention anything about whether the graph has already been connected, whether all the nodes are correct, whether all the nodes are connected or not. There may be one node that is not connected. It is still a directed graph. It is still, you can still create like a meta graph where the single node is like kind of isolated itself. It's kind of isolated outside everything else. So do not make any assumption about the structure of the graph. And then we apply the Explorer algorithm, which has been covered during the lecture. And on the meta graph we have created, starting from the source SCC, the single source SCC that we have, right? And by the way, for looking for source and sinks, just pay attention. Try to make things a little bit easier. right? You don't have to like linearize that, use pre and post number. Just basically count the number of incoming edges for each node, right? You can do that using one pass, right? Passing through all the node and all the edges using just one pass, right? Don't need to like run pre and post. That way, like it'll be kind of complicated and the code will be pretty long, and sometimes like it's just the readability is so poor and people just don't like that kind of code. So we find the SDC, we find a source, a single SDC, and we run explore algorithm on that, and return whether all the SDCs, whether all the nodes has been visited or not. If they're been visited, we return true, otherwise return false. Pretty simple, right? So the question is kind of like abstract, but if you decompose, if you try to like make it more, if you try to basically find what this question want us to do, it's basically want us to turn the graph into metagraph and find the source, to see whether there's more than one sources, then the question is quite simple. All the algorithm has been provided during the lecture. You don't have to write any kind of implementation for that, right? So for graph algorithm, reduction is more recommended. But if you're confident with your coding capability, then you're very welcome to write your own code. I mean, but like writing pseudocode, the problem writing pseudocode on Grayscale is basically like you're not writing something on a text, you're writing something on the website, and sometimes like the indentation of the code will be kind of horrible, or like, yeah, so it's sometimes the readability is not that good. So this is basically the graph algorithm. I think this is probably the hardest kind of question you will encounter for your final. And for question number 2, as I mentioned, as a question number 2 of like a sample final, as I mentioned, you don't have to like follow the logic of that solution. You can use your own DFS or BFS algorithm where you keep track of the depths, like you keep track of the distance from the starting node. Very simple. Okay, so let's take a look like the greedy algorithm next. This is the next topic we have. So for the sample practice final, question 4. I guess a lot of you guys might found the notation is not horrible, like hard to understand, something hard to understand. And that greedy algorithm, that greedy question is some kind of like different from what you encountered before. So basically what you encountered before is to find something, find the optimal value of something. And for this, it is basically want to prove that you can find something. You can basically find a perfect matching, right? It's kind of different. So let me go through that real quick. So here, basically, this is the question that you have like for the practice final, right? So let me explain what is a matching and what is a monotone matching. So matching is basically, so basically for this question, we have like some nodes in the left, some nodes in the right, and some edges that connect the left nodes to the right nodes. So this is like basically like this. This is the graph we have. And for a matching, it's basically every single for every edge along in this set, in this edge set, there are no two edges that share share common vertices. So this is like a matching. This is okay, but this is not okay. This is not okay. This is not a matching because these two edges share a single common edge vertex. And what is a monotone edge? I'm sorry, monotone matching. So basically, it is like this. There are no intersection between each one of these edge. There is a nicer mathematical form expression, but I think the notation is horrible. It's not horrible. It's like hard to follow in a very short time. So I just use a visualization. It makes things like easier to understand. So this is like a monotone matching. So if there's something like this, then since there's an intersection here, and it is not a monotone matching. And what is a perfect matching? A perfect matching is basically every single node in the left has like kind of like monotone matching to one of the nodes in the right. So this is like the monotone matching we have. If every node, if the number of edges is actually L, which means every single node in the left can find a matching and it's a monotone matching, then it's a perfect matching. So perfect matching is monotone matching in this question, in this specific question. So let's take a look at the question. The question, like, I think the candidate strategy is basically very easy to follow. Question 1A and 1B is basically about providing counterexamples, right? So for question, I think it's for D, we basically want to show that if there is a perfect matching in this graph, the assumption is very important. If there is a perfect matching in this graph, so at least we can find a perfect matching. And using the greedy strategy, we can for certain find a perfect matching. And for me, I use greedy stays ahead. So what I do is basically I have like GS, which means G1 and G2 and to GL, and OS is basically O1 to O2 and OL. So for greedy stays ahead, the very important step is try to define a kind of like the progress measure and try to align, try to like sort each step of the greedy strategy so that it can align with other strategies. This way you can like compare it easily. So for GI, it means the index in the right node that is matched with the ith node in the left. So for example, this is, for example, if we say this is the ith node, I'm sorry, this is the third node in the right, then if the third node is connected to the third node in the right, then basically G3 equals to 3. Let me give you like, I'm sorry, we should do that. If like the third node in the left connected to the fourth node in the right, then G3 equals to 4. This is basically what GI means. This is very important. Do this definition at the very beginning when you're trying to use like greedy stays ahead. And our objective is basically want to show that GI is less than or equal to OI. So basically it means the index that the ith node, that index for every node in the left, connect the index in the right node that is matched with the ith node in the left will be less than O of I for you when we're using greedy strategy. I think it's kind of like the hard to follow, especially for this poor notation. So for base case, since what the base case is, we basically find the first, node that we can in the right that we can connect it with, that we can match with, right? So G1 is 100% less than O of 1 for the base case. Since if this is, I'm sorry, if like if there are two nodes, two edges here, G1 will definitely take this node, and O of 1 maybe take this, and this is another like valid solution, maybe, right? This is another solution, but G of 1 will always take this one. So G1 is definitely less than O1. And we use induction hypothesis is basically this step. We want to show that GI is less than OI for OI, where I from 1 to n minus 1. So for the end step, GN will try to find the end step of the greedy strategy. With GN will try to find the first node in the right side in R. This R basically means right side in R after VGN minus 1. After VGN minus 1, that UN can connect. Can connect. Like so for basically we have already shown that because the induction hypothesis VO minus 1, the n minus 1 node that other strategy connected with is definitely well behind the n-1 node that greedy strategy connected with, right? So basically we have more options here. We will basically, for the worst situation, we will choose exactly the same step as other strategies, but we have like some other options here. Just wait a second. So O of I is kind of similar to G of I. G of I is the index in the right node that is matched with the ith node in the left using greedy strategy. So O of I is the same. It's just the index in the right node that is matched with the ith node in the left using other strategy, all kind of valid other strategies. Like the strategies is basically any kind of strategy you have. So this is O of I. So basically, let me just slow down a little bit. If this is Vn-1, right? This is Vn-1. It is connected with Vgn-1 here. And let's say this is, let's say for VO, for using other strategies, other kind of strategies, we say this is the connection. The n-1 node in the left will be connected with this node on the right. And using the induction hypothesis, we already know that this node will be after this node, right? So for the nth node in the left, for the nth node in the left, we can if we're using greedy strategies, right? We can consider all the nodes here, right? But for other strategy, for other kind of strategies, they cannot consider all the nodes here. So if there ain't any like connection between Vn to any single nodes in this place, then for the end step, the greedy strategy will take the same, will make the same decision as other strategy. And so basically, this is what this line means. So the worst case, Gn equals to On. I mean, the question is kind of hard to follow. So what about we just look at the greedy algorithm question that I have prepared, which is kind of easier to understand. So again, it's number 2 in greedy algorithm, and question it's like kind of like modified question from the pre-printing that I mentioned during discussion 8. So basically, what a question means is you're given a list of words, and these words have like positive lengths with W1, W2, and Wn, and they must be printed in order. And for greedy states ahead, isn't explain the base case sort of similar? I don't think so. So for the base case, it's basically we're trying to. The base case is usually determined by the greedy strategy, right? Because the greedy strategy in like for the sample final question, the greedy strategy basically is we look for the first right node that we can connect it with, right? We basically look for the first right node that we can connect it with. Oh my God, I'm just reading. If there are multiple connections here, right? We just basically, we will always choose this one since this is a greedy strategy, right? And for other strategy, it will like either choose this one or this one or this one as long as it can make a valid solution, right? So I think the first step is usually determined by definition of your greedy strategy, of your kind of greedy, of your definition of the greedy strategy. So let's take a look at this question. So this question is it's not that hard. it's kind of simple, but the way you need to prove when you're using greedy stays ahead, how you prove like the optimality of the greedy algorithm is very important. When you'll see about that later. And so basically a pretty printing problem. You can like take a look at the discussion 8, like for like modified version of like the pretty printing problem. In that problem, you'll use like dynamic programming instead of the greedy algorithm. So you have like a list of words, so you need to print them, and we assume that m is the number of characters each line can hold, and m is definitely larger than maximum of W1, W2 to Wn. And the total cost will be the sum of empty slacks or empty space in each line. And the objective of this algorithm is to minimize the cost. So for example, suppose we have the words, this is a sample list, and m is 7, and if all the characters have the same size, which is 1, and we don't count any spaces. So we would have list 42164, and 4 is basically the length of this, 2 is basically the length of is, and 1 is basically the length of a. So the following line will probably give you like, this is a, like, and you could break them up as oh sorry, this is a sample space list space, right? And in the above example, the slacks are 0, 1, and 3, and 0, 1, and 3, and then the total cost will be 4. Oh, let me reshare my screen again. Okay, so the candidate strategy we have is we place as many words as possible on the first line while the total is less than m, right? So basically, we put as many words as possible, since we have to put every word in a specific order they come, right? We cannot like put this first word and the third word, we have to put them in an order. And then we move on to the second line and repeat until all the words has been assigned. So several steps you need to make for exchange argument. For exchange argument, first step, define OS prime, show that OS prime is a valid solution. So this part is basically to justify why in OS prime, all the lines have less than m total characters. This is very important. You might need to, you might be asked to provide like kind of like justification for that. And the second, then is OS prime less than OS and applied induction. But I think for this question, OS using exchange argument is not that kind of good. It's, you might encounter some problems when you're trying to do that. Like, you're encouraged to do that after this discussion session, but I'm basically going to talk about greedy stays ahead. So for greedy stays ahead, very important thing is define the progress measure, right? To define some way of ordering the choices of OS to line up with GS. So assume we have n words in total, and assume that GS is, let me just start sharing my screen for now. So assume we have like n words in total, and assume that GS is basically G1 to G2 to GN. And this is kind of like tricky. So instead of like for when we're like designing, like the usual thing we would do is like the first G1 to G2 and GN is basically the cost, like where we should put each one of the words, right? I mean, the GS should be something related to the number of words. But here what we define GI is denoted as the number of words that covered in the first I lines using greedy strategy. So it's kind of like different from what we usually do. What we usually do is basically we say, like, since we have total of n words, right? We assume we have total of n words. And we define G1, G2, GI is basically, maybe we can say GI is the cost for the first I words, for the first I words. But here we kind of like change the way we prove it. We say that GI is the number of words we have covered in the first I lines. And in the first I lines using greedy strategy. And we also assume that OS is basically O1, O2, O of M, where OS can be either any valid solution. So O1, O2, OM is basically the number of words that has been covered using other solution in the first I lines. And one thing is we can use like induction to show that if we're using the greedy strategy, then the number of lines we will use is definitely less than the number of lines we will use using other strategies. So we can make we can say n is for sure less than n, less than equal to n. This is basically the second thing. We can use induction to prove that any other solution OS, it will take more lines. And the progress measure is we want to show that GI is larger than equal to O of I for all I. This way it is equivalent to say that within the first I lines, GS will cover more words and more characters, which is also equivalent to say, since in the first I lines, right? Since in the first I lines, the number of total characters that the first I lines can carry is I times m, right? And if we can cover more words in the first I lines, then that like it is equivalent to say the cost of GS is less than the cost of OS, since we have fewer spaces in the first I lines, right? This is the kind of like the progress measure that we define in this specific problem. It's kind of like different from the usual way we define the progress measure. I can show you another way of defining the progress measure, and you will see you cannot prove that using induction. So for each step, we use the induction to show that the cost of the GS is always at least as good, if not better, than the cost of OS. So the base case is G1 greater than O1. This is basically the question that was asked before, I think. What is the base case? So for the base case, it's usually defined by our greedy strategy, right? In our greedy strategy, we will cover like in the first line, we will cover as many points as possible, correct? So G1 will be larger than O1. Since the definition is G1 is basically how many words that the first line can, how many words that the first line can cover using greedy strategy, right? So since by our greedy strategy, we'll put as many words as possible. So G1 is definitely larger than O1. The induction step is first we define the induction hypothesis. Induction hypothesis basically will assume that GI is larger than equal to O of I for I from 1 to n minus 1. Usual like very standard way of doing that, right? I want to show that Gn is larger than O of n. What that means is basically the first n lines that using greedy strategy, the first n lines will cover more points than the first n lines using OS other strategies. And we have to analyze the n step, the n step by case by case, since this is kind of like the different. If we want to like the proof like the induction step, we need to analyze this this n step by step. So are there any questions so far? Like I've been talking a lot, so see whether like everyone understand like the. Okay.
So in your
let's move.
induction step, I have a
Yeah.
question. So in your
Okay,
induction step, how is that different than like you're just saying at the base case, the greedy strategy at the first decision will make the most, like the best decision?
Okay. So in the base case, since we only have so your question is what's the difference in like use induction step using induction hypothesis than just basically proving the base case, right?
Yeah.
So the base case is basically the first step you will take, right? It's generally like defined by the greedy strategy. But for the induction step, you assume the induction step will have like some kind of like difference because for the greedy step, you do not have any. I'm sorry, for the base case, you do not have any steps before that, right? You're basically starting with you're starting at the very beginning. You do not have any lines before that. But for induction step, you need to consider if, for example, if for the ends line, right? If for the ends line, well, and for the ends line of for GN, well, it still cover more points than using other strategies. For the base case, it's just like let me try to. It's just like you are providing a concrete example for proving base case, right? But for induction step, you are basically proving something more abstract. You're assuming something as a precondition, and then you want to prove that using this precondition, GN still holds. The relation still holds. I think that is basically the difference between base case and induction.
So how does assuming all the steps before the nth step, like how does assuming all those steps before it will be more optimal? Like how does that help you prove that the nth step is going to be the best decision?
Yeah, this is basically what I'm trying to cover. So let's like let's like analyze this problem case by case. So I haven't like go write this down, but I will probably leave that to you. So assume that for the greedy strategy, right, the first n lines have already covered all the words, right? Then like I'm sorry, the first n minus one lines have already covered all the words, right? Then we don't need an nth line, right? And since OS, right, OS like I'm sorry, since OS have already since OS like the first n minus one lines, OS cover fewer words than GS. Then that means like if GS has already covered all the points, then OS still needs to at least go on, right? Since GS already covered all the points, but OS might not have covered all the points. Still, for OS, there might still be n minus one lines, right? Yeah, for OS, there still need to be n plus one lines. So since GS already covered all the points, then GN is definitely larger than ON, right? Since GN is basically all the point, so if we have covered all the points, so GN equals to the number of words we have, and ON is definitely less than or equal to GN, correct? And if GN hasn't covered all the points, right? And then by our greedy strategy, right, we will cover as many words as possible in the ends line. While for O of n, it just basically cover kind of other strategies. So G of n will still cover more points than O of n. Just basically we just divide. We analyze the end step case by case. If like GN, if like using greedy strategy, at the end step we have to cover all the points, then GN is 100% larger than O of n. But if we haven't covered all the points, then since by the greedy strategy, we will cover as many points as possible in each line, and G of n will cover more points than O of n. Well, I'm sorry, in the nth line, like using greedy strategy will cover more points than we're not using greedy strategy, then we're using other strategies in the nth line. So in these two kind of situations, G of n is for sure larger than O of n. And since what our definition is, if g of n is greater, if g of n is greater than equal to O of n, that means the first n lines we covered more points. Then basically it means we have fewer empty spaces, since like the number of like total spaces in the first n lines is set, is basically n times m. So that means we have fewer empty spaces. And therefore we show the candidate strategy is optimal. And the importance of this question is you can try like another way of like proving the greedy strategy. You define like G, you again like define, assume we have n words, right? Assume we have n words. And if you define like greedy, if you define the progress measure like this is, sorry, G1, G2, blah, 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 Gn, since we have n words, where G1, where Gi basically means the cost of the first ice words, not ice lines, ice words, the cost for the first ice words. Then you are like getting into trouble when you're trying to prove the induction hypothesis, when you're trying to prove the induction step. Try that yourself, and then you will see what kind of like the problem you will encounter when you're proving induction step. We can discuss it later, like at the end of the discussion session. And I just want to cover divide and conquer since we're a little bit short on time. So for divide and conquer, the first like the question is that you are strongly recommended to take a look at practice final question 3. And so the thing is here, the one thing I want to like make kind of like addition to the solution. I think the solution makes a point, but it kind of like neglects some of the important thing, that why we're always trying to go for the half of the array with a 1 at the beginning and 1 at the end, right? Why we just keep chasing that array, right? This is because if there's an array and its length is the power of 2 and the length is larger than equal to 2, and the first and the last element, if the first and the last element is 1, then this array will have 2 consecutive bits for sure. This is why we keep chasing the half. Well, this is why we when we decompose the whole array into 2 halves, like first half and second half, and we keep going for the half with this kind of like structure. We can use proof, and we can like prove by contradiction. We can assume there are no consecutive bits in any array, in an array with even number of elements. And then if the array starts with 1, then the structure will 100% be 1 0 1 1 0 1 0 1 0 1 0, right? Where the last bit is 0 for sure. And this actually contradicts with the condition that we have, that this array start with 1 and end with 1. And this is why we keep going for the half with that kind of structure. This is very important. And for divide and conquer, the problem is it's basically when you find something, when you like find like that there's a strong connection between each one of these elements, there is very strong connection, that you don't have to search the whole thing. When you search the middle, or when you search the middle of an array, and that array can tell you which part you should keep searching, then you should probably think about using divide and conquer. And let's take a look at the second question. Find local minimum in the array. And what is local minimum? The local minimum is basically a number whose neighbor are greater or equals to its greater to itself, and we assume there are odd integers are distinct. I'm sorry, not distinct. I'm assuming that like there will like every integer is different than their neighbors, so we don't have like kind of flat situations. So local minimum in this graph is basically 2 and 3. Since 3 is less than 9 and less than 4, and 2 is less than 5, and 2 have nothing on the left, so 2 and 3 are 2 local minimums. And the question is, want us to just return any one of the local minimum. Correct. Let's take a look at naive approach, right? Naive approach is time complexity, the time complexity of n. We just go through every single node in this array, and we see whether and we see whether it is a local minimum, right? But we can actually do that using we can actually design a better algorithm with a better time complexity. If we're looking for like one of the local minimums, and we try to apply divide and conquer on this problem, can you like figure out a better algorithm? Since remember, we only require to return any one of the local minimum. We are not required to return all the local minimums, right? So this is, I'll leave that to you. I didn't provide any answers for that question. I'll leave that to you, so for you to look at that. Very interesting question. And this question is a little bit hard, like find the case largest element in an array. So I have explanations, examples, explanation, and my own source code for this question. It's written in Java, but I guess most of you can understand the code. So it's basically how to use constant linear time to find the case element inside an array. And again, this kind of algorithm use like divide and conquer, the concept of divide and conquer. And it's basically similar to, I'm not sure whether the professor covered that in the lecture. It's basically similar to quick select. And the naive way to do that is basically you sort it first, right? And then you find the case largest. But that will take you O(n) log n time. This is something we want to improve. We want to do that in O(n) time. So basically, this is the explanation here. I think because the time is a little bit tight, so I will leave that to you guys to understand what it means for each part. So let's take a look at dynamic programming. I didn't like provide any dynamic programming questions for specifically. So take a look at final question 5, and also like take a look at the discussion, at the recording of the discussion 8 and the slides of discussion 8. Since for the pretty premium problem that we had, right? And right now we want to make some modification on that. We want to change the penalty. The cost is the number of extra spaces in each line square, the sum of the square of the number of extra spaces in each line. So basically, for the previous problem, if this is the case, then the sum will be 0 plus 1 square plus 3 square, which is 10. And then you can see like this question can no longer be solved by the greedy strategy, and you have to use a dynamic programming to solve this problem. I covered this problem in the last discussion session, so you can take a look at that question, and I mean you can take a look at the recording of that question. So why can no longer be solved by the greedy strategy? We just simply change the cost, right? So for a more intuitive intuitive way of understanding this question, and why is basically in before when the cost is basically a linear function of the number of extra space in each line, the question is more like a kind of convex or concave question in optimization, right? You can try to find the optimal solution in each subproblem, and you just keep climbing, and you will find you'll finally find the optimal value. But when we have like a square here, the question is no longer convex or concave. There might be like some kind of local optimum and local minimum in this question. And if you still use greedy strategy, it's like it's like gradient ascent or gradient descent in optimization. If you still using greedy strategy, you can only guarantee the local optimum instead of the global the global optimum. The recording of the discussion 8, I think, is in the post. It's in the it's one of the Piazza. It's on one of the Piazza posts. I think it's pinned. Let me give you the link to that. And also all the materials, well, and all the like discussion materials have been uploaded to the same file you download the current materials. So in like the probably last 5 minutes, I just want to cover like what I mentioned here in this question, in this greedy question. The progress measure, just a few minutes before we end this session. Let me share the screen. So, as I mentioned, I use like the first I lines to prove the optimality of the greedy, right? But the more common way like people would first think about it is using the first I words. So we're given I words, right? And as I mentioned, greedy stays ahead. First step is to develop a kind of like the progress measurement, right? GS, G1 to G2. I'm sorry, given n words. Oops. GI, G2, blah 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 to GN, right? We have n words, and the usual way like people think is like defining greedy, defining progress measure is GI denotes the cost of the first I words using greedy strategy, right? This is the normal fit. This is normal definition. And OS is basically O1, O2, blah, 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 ON. Just then where OI denotes the cost of the first I words using other strategy, correct? And right now we want to use like greedy stays ahead. So base case, G1 equals to O1, because for the first word, we will still put it in we'll still put it in the first line, right? We'll put it in the first line, and the number of extra spaces is the same. So G1 equals to O1. So here G1 is the cost, to be sure. And induction hypothesis, Gn minus 1 larger. I'll just like make it G minus n minus 1. I'm sorry, less than. So that means like I should use GK less than OK minus 1, right? And we want to prove that GK is also less than O of K. That basically means the first K words, the cost of the first K words using greedy strategy is less than the cost of the first K words using other strategies, right? But can you prove that? Like, let's like analyze the situation case by case, right? So given that, let's say if like there are the first K minus 1 words, if this is the situation, we have like number of lines. If this is the K minus 1 words, if the case words, if using greedy strategy, the case word can be fitted into the same line that the k-1's words located, right? If we can fit the case words here, then g of k is definitely less than O of k, right? Since g of k is like originally less than, I'm sorry, since gk-1 was originally less than OK-1, and right now gk actually decreases by a certain amount, right? But if like the k minus if like this line cannot hold this word, and you have to use a new line, right? Then gk actually equals to gk-1 plus m minus the length of the i's words. Then length of the let me say word I. I'm sorry, word k. Bad notation. Correct? This is the equation. But for O of k, we don't know the structure of O of k, right? We know nothing about like whether the case words in. We know nothing about the cost of the first where the case k-1 words be located if we're using other strategy, right? It could be like this. It could be like for example, this is the case word. This is OS. It could be like this is the k-1s where the k-1s were located. It could be the kind of a situation that the case word using OS can be fitted in the same line, right? Then this is then O of k will be less than OK-1, while G of k is greater than GK-1, right? Then we kind of like stuck at this point because we don't know the structure. We don't know where the i's word will be located, right? It could be it could be located anywhere. We don't know that for sure because we only know the cost. We only know that the cost for the first I words, well, for k-1 words will be less than the cost of using like other strategies. Correct? So this is kind of like the problem you might encounter if you're using this way of defining the progress measure. Yes. That's, I mean, my notation is not that kind of mathematical. It just basically using like computer science languages. You can see I'm not like a math major student, but for proving the optimality for greedy strategy, you need to include like several things. Like basically, what kind of what do you want? How are you gonna like prove this? Optimality using greedy states ahead, or using the upper bound, or using the exchange argument, right? You do like first states that which kind of method you use, and then you need to include the base case if you're using greedy states ahead, and the induction hypothesis and the induction step. And for the exchange lemma, you need to first define OS prime, and to show that OS prime is larger than OS. And basically, I provide I think in the previous PDF file I gave you, it clearly states like the procedures you should use for greedy states ahead and the exchange argument. So follow that. You don't have to use very precise mathematical languages, but you have to include those steps at least. Yeah. So I mean, like the last explanation might be a little bit hard to understand. So you can try that yourself without using the way I prove it in the PDF file I gave you. You'll get into trouble since you'll basically see that like GK, there might be a situation that GK is larger than GK minus 1, but OK is less than OK minus 1. Then the induction hypothesis only gives you GK minus 1 less than OK minus 1. But you cannot use this to prove, but you cannot use this condition. If this is the condition, then you cannot also prove that GK is less than O of K. Since something, this is increasing, this is decreasing and this is increasing. So just kind of like you'll get into trouble if you're proving this way. So the final suggestion is how you define the progress measure is very important if the question is kind of hard to prove. Okay, so that's basically everything for today's discussion session. I think there will be other sessions, other review sessions hosted by my colleagues. So feel free to join. Feel free to join that other sessions, and I'll stay here for like another 5 to 10 minutes to answer questions.
Hey, can I ask a question about the first problem that you presented, like the problem related to how to find whether there's a path in a graph that can traverse everywhere?
Yeah.